Come on in, everyone. Come on in, everyone. Feel free to ask me any questions. Sorry it took a little longer to get online than I expected. Anybody have any questions before we get started? Today's the 6th, right? Yes. Do that. All right, so I got that ready to roll. Okay. So no one's typed any questions, and no one's asked any questions, so I assume we're all good to go. Last time we worked on problems involving convection and radiation using the dq over dt equals ka delta t over L formula, which is a convection, which explains how convection works. And then we worked on the stuff on Boltzmann law for radiation, which was basically dq over dt, which I warned you all that that's also the equivalent of luminosity in astrophysics and astronomy. It's basically the total output of energy per second. By a star, for instance, or for any other heat source, and that's equal to the emissivity times the Stefan Boltzmann constant, which is sigma, times the surface area of the object times the temperature of the object to the fourth power, and that has to be in Kelvin. So we did do all that. I showed you a couple problems working. I showed you how basically a single human in about a 70-degree room is equivalent to 175 to 120 watts, basically, and that's why you know gyms, lunchrooms, auditoriums get kind of hot after people log in. All we have left now, at least regarding thermodynamics, is chapter 20, and most of the teachers at TCC usually chose not to do 20 at all. I'm one of the few that prefer to do 20 just because I can't see teaching any kind of thermodynamics without the second law of thermodynamics, which is the one that's so often used in charlatan. So often used by charlatans, people claiming things that aren't true and claiming things that are true that aren't true, stuff like that. Snake oil salesmen and the like. Uh, if you would like to learn a little bit more about that, I'd suggest you follow the Skeptic's Guide to the Universe, which is a really good podcast that reports weekly about science. It's supposed to be a 1 hour podcast, and I don't think they've ever been able to edit it down to less than an hour and 20 minutes. But I listened to it for about 12 years, and it's great. I haven't been recently listening to it. Actually, I haven't paid that much attention to it since we got. No problem, Nathan. I haven't paid much attention to it since Rebecca Watson left, who was one of my favorite. And it's not that I dislike Cara Santa Maria, but just letting you know. I was there before one of the board members died. That was terrible. But it's basically three brothers, Cara Santa Maria, and a fourth guy, Evan, who's their friend. So, anyways, check that out if you want. What I wanted to do is go over chapter 20 specifically. What I expect of you, and really, it's I'm sorry I keep yawning. I don't know if I can't stop it. But it's a very short chapter in terms of what I want to cover, and I've gone through and taken the time to highlight the things. So I think it might be best if I go ahead and share my screen with you guys. So I'm going to go ahead and
I have a question before we get started.
yes, go for it.
Are we going to do the chapter homework's due tonight for 20 and the conceptual?
I just checked. It's not supposed to be due till the 12th. Let me double check again because I literally
Maybe
was
I got the
there.
wrong. Maybe I got the wrong day on there. I don't know. Let me look.
Yeah, it says the 20th is due on 2/12. Chapter
Maybe.
20.
Oh gosh. Okay,
Today's
I
the
may have.
6th. Gotcha.
I may
19
have.
was due last night.
Oh, I've already done 19. I got the weeks mixed up because of the numbers. I get my numbers mixed up.
Gotcha. Well, while I'm here, did anybody have a problem getting chapter 19's part 1 and 2 done by yesterday?
No.
You didn't? Anybody else in the class? Feel free to write it in chat if you did.
Okay,
All
hold
right,
on.
looks
Let
like
me see.
nobody did, so I'm not gonna. I was considering setting that date back if they needed another day, just to be nice, but it doesn't seem to be.
Obviously, it's not sponsored.
God, I can't stop yawning. Oh, okay. So let me start off by sharing my screen. I'm going to share the screen. This is actually a view from the book. So let me do share screen.
Is a good.
Okay. Sorry. Sorry, I forgot to turn off the.
I was wondering if all that noise was coming from your place. It was loud. All right, so this is chapter 20. It's called the second law of thermodynamics. What I wanted you to see is obviously section 20-1 is the second law of thermodynamics. Just an introduction. 20-2 is heat engines, and I don't need you to know all about heat engines. I need you to be able to calculate specifically the efficiency of any heat engines if I at least give you the heat added to the system or the heat extracted from the system or the work in place of one of those, that's acceptable as well. So you should be able to just calculate the efficiency. I'm going to give you a formula for that. And then you should be able to calculate the efficiency of an equivalent Carnot engine. Those are some of the main problems that I think you should be able to do. And I've even gone so far as to highlight very specific examples in the chapter. You'll look and they should be highlighted in your copy of the book as well, because not only did I highlight them, I shared it. So you're supposed to be able to see it from your side. So far as the heat engines go, in general, any heat engine, it's going to take in a certain amount of heat, and they normally call that QH. It's normally taken at a temperature TH, and it's going to expel non-useful heat, and they call that QC, and that's usually expelled into a heat reservoir of temperature T sub C, and it puts out an amount of work W. But conservation of energy dictates that you really only need two of those quantities, whether it be QH and QC or QH and W or W and QC. Doesn't really matter too much. You can get the efficiency of any engine, any heat engine from those numbers, and I'll explain to you how. And then the Carnot efficiency, your book does a lot of work using the results that we got from the last chapter. Okay, go again. Using the results we got from last chapter, it takes some of those results and then works through a good long derivation regarding the Carnot engine just to get an equivalent relationship for the efficiency of the Carnot engine. And that one's purely in terms of low temperature and the high temperature. In other words, the T cold and T hot or TL and T H, whichever one you want to use is fine. So you'll need to know how to do that efficiency because I'm going to show you some of the versions of the third law, or excuse me, the second law involve efficiency of a heat engine. Then in section 23, it does specifically go through Carnot engines, reversible and irreversible processes. Then it goes through refrigerators, air conditioners, and heat pumps. Those things are not necessarily judged on their efficiency as they're judged on something called coefficient of performance. Sorry again. I think that's perfectly reasonable to ask you guys to do for homework. And I tried to fish most of it out on the practice test, but I wouldn't be surprised to find a couple of coefficient of performance type problems in that. But I am not going to test you on refrigerators, air conditioners, and heat pumps and coefficient of performance. Okay. I will bring up entropy and mainly because that's one of the versions of the second law of thermodynamics that uses entropy. So you got to know that entropy in the second law of thermodynamics, order and disorder, unavailability of energy, the heat death of the universe, statistical interpretation of entropy. That is the result I want you to know, even though I'm not going to make you necessarily do anything with it on the test. thermodynamic temperature, the third law of thermodynamics, which is another law you should know, in addition to the zeroth law, by the way. So you might want to jot that down, the zeroth law of thermodynamics, the first and second law, and the third law of thermodynamics. All are things you should have committed to memory. And I mean specifically exact wording, because there's often, I'll have like on one side of the page a list of laws, if you will, and then on the other side of the page, a list of names of laws, and you'll have to match them. And there will be like the Clausius statement of the second law of thermodynamics, and there'll also be the Kelvin-Planck statement of the second law of thermodynamics, and there'll be Kepler's third law, and there'll be Newton's first law, and Newton's second law, and Kepler's second law, and the law of gravitation. All those different things will be on there. So it's a hodgepodge of all these different laws. So you really got to know your stuff about that. And that does remind you that the course is comprehensive. So yeah, last when you took 241, you got to cover gravity and Kepler's laws. So you should still know those. Also in 241, you covered Newton's three laws of motion. So you still should know those as well. So just keep all that in mind. Let me restate them again really quickly. Actually, maybe I can do it even nicer. I'll do it in such a way that I can chat it. So Newton's laws. And when I say his laws, I mean, not only do you have to know all three of them, but you need to know of them and what they're called. So the first law has a very specific name. The second law has a very specific name. The third law has a very specific name. So you should know all of those. So under Newton's laws, I would say his first, second, third, and gravitation. That's his law of gravity, in other words. Kepler's laws, and that's his first, second, and third. In addition to Kepler's laws and Newton's laws, those all came from last semester. We'll also have zeroth, and I'm going to try to learn how to spell that. Zeroth, dot, 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 first, dot, 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 second, dot, 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 and third law of thermodynamics, and all of the forms of the second law of thermodynamics as given in your text. Okay, so I just typed all that out. Y'all can, cut and paste that into your notes if you want. The main thing is, yeah, I expect you to know those and expect everybody, not just your 242 class, but every class. It does ultimately talk about thermal pollution, global warming, and energy resources. I usually like to discuss global warming. I'm a little bit tight for time though, but you're welcome to check it out on my YouTube channel. Specifically, some of the astronomy lectures I gave, I did a lot on global warming. I will tell you this. That's probably the most important thing. For one, there's no such thing as a global climate model. That's not what they use. They use something called uh, a global circulation model, and the global circulation model has various outputs, and some of the outputs are, for instance, the climate. So you can find out the climate in general, but that also includes the average temperature of the planet, stuff of that sort. And those global circulation models are basically based not on, curve fitting to the past or any weird stuff like that. They're based on simple things like uh, the laws of physics. You can't destroy energy or matter. You can't create energy or matter. It envisions the Earth as having a very specific surface where some, 2/3 of it literally is water, and then it uses what we know about how water interacts with energy to take into account the fact that the oceans and the lakes and streams and things like that, all of those have some role to play in carbon dioxide, methane, carbon monoxide, ozone, all that stuff. All those sort of properties that we've learned from science are taken into account. Uh, in fact, most recently, some of the predictions where we predicted the globe would warm faster than it did were mostly because of our lack of understanding specifically about how much of the ocean or how much of the heat the ocean would be capable of absorbing. We actually thought quite a bit smaller fractions of the heat would be absorbed by the ocean, and that the air temperature would climb faster than the water temperature did. But in fact, if you read the uh, reports that are put out by the climate committee, the international IPCC, in other words, basically you'll find that they do watch that. They report back every year. They report which models are working best, which models are working worse. They reassess which ones they were going to run by, and they use those. They tell their failings, they tell their successes, and they even tell you, hey, it looks like we, underestimated the amount of heat that would be taken out of the environment and atmosphere and taken into the ocean, and therefore we've had to revise our calculations downwards. But that also made another problem. Specifically, the tides are rising a lot quicker, and that's because more heat went into the oceans than we expected. So that's the kind of give and go that they do. Uh, yes, these global circulation models have been tested before. In fact, Carl Sagan was one of the first people to write a global circulation model. It's my understanding he actually did it for his PhD thesis. And in fact, he predicted a lot of things about Venus. And later, when we got to go there, we found out that most of what he predicted was right. We've done those for Mars. We've done those to some extent, though it's a little bit different for areas like Jupiter and Saturn and stuff like that as well. Uh, we've We've also taken those same global circulation models and we've used those to predict what we already knew happened. So you can take, for instance, data that we had in the early 1800s and substitute that into global circulation models. And basically, one of the fundamental tests of whether a global circulation model is worth a crap or not is, does it predict what we know already happened? And if it doesn't, it gets thrown away. So yes, the global circulation models have been used and have correctly predicted stuff. And if they didn't, they wouldn't have been used at all. They would have been thrown out. They wouldn't even got maybe would have maybe allowed a student to get a master's or a PhD thesis from it, but that's about it. And even then, not necessarily. Then there's a lot of tests where they make sure it doesn't, violate conservation of energy or conservation of mass or any kind of stuff. It agrees with the science of meteorology and so on and so forth. So that's the kind of stuff we're know about with regards to global circulation models and why the Earth is increasing in temperature. The globe is changing, the climate is changing, and essentially 99+% of the people that specialize in this area believe that yes, it's absolutely changing, and yes, it's absolutely due to human things that humans have done, and it's more a debate about whether it's, you know, 95% versus 91%, or maybe 92%. Judith Curry is the only one that I know of that's actually fairly, oh, I shouldn't say fairly. She's way more knowledgeable about global circulation models and climate and stuff than I am. But she's the only one that really is sort of doing anything like sounding an alarm saying we shouldn't do A, B, or C. And even then, she's mostly not complaining that the results are wrong, but more so complaining that we might be doing a little too much because we don't necessarily know the positive aspects of global circulation models and global climate change caused by humans. Okay, so if you're wanting to look for a naysayer to find out I would say lately, since she's gotten off of, since she's emeritus at Georgia Tech, she's a little less or a little more unhinged, I'd say. But you can find her on Twitter. You can also find Michael Mann. You can find a lot of people on there, and that's one of the reasons why I still use what used to be called Twitter. So, anyways, we also have some pretty conclusive evidence. For instance, we know how much the CO2's gone up since, even the pre-industrial era. And if there was just some way we could tell what fraction of the CO2 buildup in our atmosphere came from fossil fuels as opposed to naturally occurring things like volcanoes and stuff that causes this. And that is a big thing. In fact, you can see volcanoes actually can cause the global climate to change as well. And they're not something we predict. So sometimes they come in and make the globe a little worse off than we expected, and that wasn't our fault. That was obviously just nature. Well, in some cases, we might believe some of the. Uh, there is some arguments to be made right now that some of the tectonic activity, which also can lead to volcanic activity, may or may not be partially caused by humans and what we're doing. So just I'll leave it at that. There's a lot more science to be done on that, but fracking, for instance, is something that's showing to destabilize a lot of geologic structures. So I just know that's an active thing that they're considering. But if we only had some way of knowing what CO2 came from natural causes and what CO2 came from non-natural causing, well, guess what we do? And this is what you're not going to hear on Fox. The only place I've heard it on is BBC, NPR, and Skeptic's Guide to the Universe. And science places basically. I haven't heard Fox, I haven't heard MSNBC, I haven't heard CBS, ABC, or NBC ever state these. And maybe they've done better by now, but they hadn't done it for the first 20 years I started watching this. But yeah, guess what? We did this. We've discovered that in fact the modern day estimates of CO2 in our atmosphere are deplete of carbon-14, which is the one that decays. We use it for carbon dating and stuff like that. And that's because if you think about what global warming is supposedly caused by, i.e., the burning of fossil fuels, then you'll know that we're burning fossil fuels, and fossils were things that died millions of years ago, and we're getting the carbon from them. And having died millions of years ago, they haven't taken in fresh oxygen and atmospheric gases, which includes carbon. They haven't taken that in millions of years. Therefore, they have almost no carbon 14 because the carbon 14 only has like a 5,360 year half-life, if I remember correctly, somewhere around there. It's less than 6,000, more than 5,000. And the rule of thumb is, 3 to 5 at best half-lives. And once those have gone by, none of it's left. And lo and behold, it looks like 98+% of all the CO2 that's been added has no carbon 14 in it, no radioactive nuclei in it, and that would be indicative of it all coming from fossil fuels as opposed to coming from volcanoes and other natural processes. So that's enough, I think, to tell you uh, what you're not being told. You probably heard 5, 6 years ago people talk about there's been no global warming in 16 years, and you think, well, that's 16 years is a bad thing. Well, guess what? That's 16 years. If you go back from the time that Ted Cruz was the last person I heard say that. If you look back, at that time, that was the record year for temperature. And it was like 1998, if I remember correctly. And so he's basically like choosing to make the case that you really, really need money because you haven't had a paycheck in 16 years. And then you look back and find out on that 16th year, in fact, you had won the lottery and got 120 million. But yeah, you hadn't had any income since then. So please send him money, right? That's what he did. He basically just, and it's not just him, it was several people. But what I'm saying is, yeah, if you go back to the hottest day and record and then measure all the temperatures with regards to that hottest day on record, guess what? They'll look like no global warming has occurred. Well, guess what? Since then, we've had that year's been exceeded, I think 3 years in a row now. So yeah, that's no longer a good point. All right, so that's enough for global warming. Let me go back and show you now. As I pull into this, the second law of thermodynamics starts off with this nice classically used picture. So here's something neat. We've learned about the first law of thermodynamics, which I told you was basically a conservation of energy. If you were to work out the details of a coffee mug, let's fill it up with coffee so we can make this exciting. A coffee mug sitting on the table filled with coffee. You accidentally bump against it. It falls off the table, shatters on the floor. Okay. Now you run the tape backwards, and we instinctively, when we're watching a videotape backwards, we can sense it. Okay, that's kind of a neat thing about us, and that's why we've ultimately called entropy times arrow, which you'll read about in this book. And I definitely highly recommend you read all of chapter 20, even though I'm not making you do any of it, most of it. But I definitely recommend you read all of it slowly, in little bites that you can without losing your attention span. But here's the deal: if you knock that cup of coffee over, it lands on the ground and shatters and coffee goes everywhere. You could actually calculate exactly how much energy it takes for all that coffee to jump up and reform in the area where the coffee mug is going to reestablish its shape and constitution. And you can take and calculate how much energy it's going to take for those pieces of the coffee mug to jump back together and assemble in that perfect shape of a coffee mug. And then that whole coffee mug can launch up with the coffee in it onto the table. And you will not find that that violates the first law of thermodynamics at all. So the first law of thermodynamics is completely cool with that process. That leaves us with a problem. We should be able to say there's a good reason for that not happening. And it turns out that reason is the second law of thermodynamics. Okay. So that's ultimately where we're going. Let me give you a more concrete example. So let's say you take a block of metal and you submerge it in water, and then you bring that water to a boil. So once it's brought to a boil, the block of metal is now 100 degrees Celsius, essentially. You have a collection of water, maybe on the order of a quarter cup or a half cup or something like that, in an aluminum container, aluminum pail, if you will. And that aluminum pail, you know its mass, you know that it's made out of aluminum. And you know the mass of the water that's in the aluminum pail, but that little aluminum pail is inside of a calorimeter so that we can restrict loss of energy to the surroundings. Uh, if we check the temperature of that water that's now in equilibrium with the little aluminum pail, if you check that temperature just before you put the actual hot metal block into the water, let's say it turns out to be 20 degrees Celsius. So right at 20 degrees Celsius, that's the temperature of the aluminum cup. That's the temperature of the water that's in the aluminum cup. And then you've pulled out and dried really quickly the block of metal that's at 100 degrees Celsius, and you put it in and submerge it without splashing into the cup of water, into the aluminum cup, and you stir it and you watch the temperature gauge, and the temperature climbs, 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 climbs. And then it starts to slow down, comes to an end. And if you wait long enough, it'll actually fall back down because then the water, the metal block, and the cup are all slightly higher temperatures than room temperature, which was 20 degrees Celsius. So it's going to start giving off heat slowly to the room. Well, if you recorded that highest temperature, maybe you found it was 22.5 degrees Celsius. Okay. So it went from 20 to 22.5. Well, guess what? You could also do a calculation and say that that block, which was 100 degrees, was stuck in 22-degree water or in 20-degree water. And that block then, being the hot object, oddly enough, actually pulled heat from the cold water that was at 20 degrees Celsius, and it actually went up to nearly 200 Celsius. And at the same time, the water, because it's giving its heat up to the hotter block, dropped its temperature down to 17.5 degrees Celsius. And if you did a conservation of energy calculation, you'd find that energy was completely conserved and that, in fact, the metal block went from 100 degrees Celsius to 200 degrees Celsius, whereas the water went from 20 degrees Celsius. The water, the aluminum cup as well, went from 20 degrees Celsius to 17.5 degrees Celsius, and energy was completely conserved. That's not violating conservation of energy. But if you do that same calculation with something called entropy, what you'll find is that the entropy actually did increase, and that entropy is a way of stating the second law of thermodynamics. Okay, so let's start off right here with the second law of thermodynamics as explained by R.J.E. Clausius, who lived from 1822 to 1888. Basically, Clausius' statement of the second law of thermodynamics says heat can flow spontaneously. That's a very important word here. Heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object. So when I was arguing that heat was actually going to flow from the 20 degrees Celsius water into the 100 degrees Celsius metal block, I was violating the second part of that. The spontaneous is the key word, though. For instance, we know that you can take your refrigerator, which probably is around 35, 36 degrees Fahrenheit, and you can pull heat out of that inside of that refrigerator, which again is at like 35 degrees Fahrenheit. You can pull that out and dump that heat into the 70-degree room that is your kitchen. That's completely possible, and that's not a violation of the second law of thermodynamics. The reason why is because that is not spontaneously happening. In fact, if you unplugged your refrigerator, it would stop doing that immediately. The reason that you can do it is the refrigerator is actually taking energy and using that to force the heat out of the cold air and into the warm air. So you can definitely do it with energy. But if you, again, checked out your second law of thermodynamics in various forms, you'd find it would not be violated by the refrigerator. So that's the key aspects of this version of the second law of thermodynamics. Remember all of these. Notice this one's highlighted in blue. I tried to do them all in yellow. I don't know why they came out blue. But anyways, you should be able to see it from your side. This is one that you should commit to memory. In other words, write it down, memorize it, be able to recognize it as the Clausius statement, not just the second law of thermodynamics, because there's going to be more than one of those. Everybody follow that? All right. So that is a version of the second law of thermodynamics. Notice it does have a little dagger down here. By spontaneously, we mean by itself without work, without input of work or some sort of energy. So make sure you read all those footnotes and stuff like that. Here's the heat engine, or a description of heat engines. So what a heat engine is, and by the way, a 2-cycle and a 4-cycle gas engine and a diesel engine are all heat engines. Okay. The motor that runs your electric, or that runs your washer or dryer, is an electric motor. It's not a heat engine, just so you'll know. So what a heat engine does is a heat engine takes in a certain amount of heat called QH from a high temperature reservoir, and it's just relatively high, meaning this temperature is going to be higher than this temperature, but it takes it from a high temperature reservoir at temperature TH. And then some of that QH is used to do useful work. That's the W. Now, you cannot use all of it. That's one of the ways of stating the second law of thermodynamics is whenever energy is converted to heat, that's sort of a bastardized version of heat, of energy, if you will. So you can't get all of it out, period. So when you convert energy into heat, there's always going to be some fraction of it that's just lost. No ifs, ands, or buts about it. That's another statement of the second law of thermodynamics, but you'd have to call that, Mr. Younger's version. It's not one you have to commit to memory. All right. So the excess heat that's being wasted basically is going to be called QL for Q low, and that's going to be dumped into a low temperature reservoir at temperature TL. Okay. In fact, one version of the second law of thermodynamics says this heat engine is not possible unless this part QL is coming out of it and ejecting QL into TL. If it doesn't have that yellow leg down there, then it's not a real functioning consistent with the second law of thermodynamics heat engine. Okay. Now you can also realize all the energy coming in is QH. So what you know is QH has to be equal to QL plus W. So that's something you can use. And what I'm going to tell you is that the efficiency of a heat engine is what you get that's useful, in other words, the W, divided by what you pay for, which is all of the energy you have to put in. So that's QH. So in general, the heat efficiency of any engine is, or the efficiency of any heat engine is the work divided by QH. So that's your formula. We use the lowercase e for efficiency. So everybody take the time to write that down. Efficiency is equal to work divided by QH. Now you can simplify that, and I'll show you this in equation form later on my iPad, but you can see it here in these equations. Since QH is equal to W plus QL, you can substitute for W QH minus QL. So then instead of having the W on top, you'll have QH minus QL on top divided by QH. And of course, QH minus QL over QH can be broken up into two separate fractions, being QH over QH minus QL over QH. But QH over QH is just one, so you get 1 minus QL over QH, and that is another form of the general efficiency of a heat engine. Okay, that's just the general formula, not the special case, the Carnot engine, which is a reversible engine and no friction and all that cool stuff. So here's where we talk about the efficiency. They actually explain how a four-stroke engine works. That's actually kind of helpful. They talk even about nuclear power plants, steam turbines, for instance, or heat engines, that sort of thing. They talk about why you actually need a temperature difference. That's something that's very helpful. That also helps you understand the heat death of the universe, which will happen a long time from now, like maybe 10 to the 20 years even. Okay. So here's the efficiency. Like I said, the efficiency is supposed to be what you get that's useful, which is just the work, divided by everything you put in. So everything you put in is QH. So you see you get W over QH. You also see, like I told you, you get QH minus QL over QH. And then, of course, breaking that up into separate fractions, the QH over QH becomes the 1. And then you have a minus QL over QH, and that's where that is. So that's the efficiency, and it'll come out as a decimal. If you want to make it a percent, you move the decimal 2 places to the right and put a percent on it, but that's neither here nor there. Okay. So notice I have highlighted, and I probably should highlight this too. Let me see. I couldn't do that earlier with single equations. It looks like it's letting me now. Yeah, it is. So that and this form. Okay, so those two equations you need to know because you need to be able to just use that efficiency for any heat engine, period. I've highlighted example 20-1, 20-2, and 20-3. That means those three examples are types of physics problems you can expect to have on the test that covers chapter 20. So far, if I remember correctly, these are the numbers. I know 1, 2, and 3 are right. I know 7's right. I'm not sure about 5, but that's what I'm thinking right now. Those are all ones you're responsible to make sure you know how to do. So you see here, they calculate a car's efficiency. An automobile engine has an efficiency of 20%. So in this case, they are saying, hey, we know E, right? And produces an average of 23,000 joules of mechanical work per second. So that's the work, and that's 23,000 joules. They said per second. We really want heat or energy. We don't want power. So you just say, I'm going to do it per second. And in which case you write down 23,000 in the numerator. And then now you've got to figure out what exactly is QH. And it says during operation, how much heat input is required and how much heat is discharged as waste by the heat engine. So we know E in 20-1A is going to be 0.20 because you do, like I said, it comes out as a decimal, so you got to put it in as a decimal. So you'd have 0.20 equals 23,700 over QH. That allows you to solve for QH, which you get 115,000 kilojoules. And then, of course, the fact that QH has got to equal W plus QL allows you to solve for QL, so you can get the 92 kilojoules, and so on and so forth. So it's a very straightforward, simple problem. I don't think anybody needs me to work that for them. It should be easy enough. And 20-2 and 20-3 are no more difficult than that as well. So in section 20-3, we go over the Carnot engine. And there's a lot of different engines you can find in different textbooks and books I have on engineering. For instance, I've taken a little bit of an interest in the engineering of internal combustion engines. So I've been buying engineering textbooks for that and working through those just for the fun of it or whatever. But you'll find, for instance, if you've ever known anybody with a really nice older Dodge truck, you might have seen that it was called a Sterling Dodge, or you might have seen Sterling with some other manufacturers. Sterling is another form of heat engine. And if I remember correctly, I think the Sterling engine was originally supposed to be a diesel. I could be wrong on that. The difference being diesels do not need a spark plug. They have such a huge compression ratio that they explode just from being compressed. So imagine taking a gas and compressing it so hard that it just explodes on its own without a spark. That's the difference between a diesel and a regular car engine. Regular car engine actually has to have a spark blow when the compression is at a maximum. Okay. But in this case, what we're talking about is the Carnot engine. And what they're trying to do is get the ideas of an engine down to the simplest parts. And here, if you start from part A, step A, notice that's on a dotted line that's labeled with the temperature TH. Since it's labeled with one temperature, that means it's an isotherm. So not only that, it's going from VA, which is lower than VB, to VB. So it's actually an isothermal expansion. So this is the case where the piston would be backing out of the chamber, and in backing out, it's actually expanding the gas. And in principle, you could actually imagine this is the part where the gas is being pulled into it along with air. Okay. Now, after that occurs, it reaches a high point, and then all of a sudden it goes to what we call an adiabatic expansion. So no heat's going to flow, and it's going to expand just a little bit more, and the temperature is going to change from T high to T low. Then we have an isothermal compression from C to D. And during the isothermal parts, notice heat flows in the first isothermal part. The second step is adiabatic, so no heat flows. The third step is isothermal again, only this time it's a compression, so heat is let out. That's QL. And then we have a adiabatic compression from D to A, which puts us right back at the starting point. Okay, that's what the Carnot cycle is, and it's imagined to be reversible. So it's like it basically has no friction, and it takes place so slowly that it's in equilibrium at every point. So it really is the most ideal idea of a battery, and I mean of a heat engine in general. So in some sense, this is the high watermark. Whatever efficiency we get from this, that would be the holy grail for all other heat engines, because this is a heat engine that's made ideal without friction and stuff. Okay. So the math isn't that big of a deal. You can go through it and work it out, and I highly recommend you do it, especially if you're interested in mechanical engineering or if you're interested in thermodynamics and science in general. This would be a worthwhile thing to do. But I really don't need you to do that. What I want you to be able to do is take the result where basically Giancoli does a long derivation and changes that formula from efficiency equals 1 minus QL over QH to efficiency equals 1 minus TL over TH. That's all you're going to do. So you just look for the temperature for the low temperature reservoir, look for the temperature for the high temperature reservoir, make sure they're in Kelvin, and calculate the efficiency. All right. Notice real processes are always irreversible. It talks about this. Basically, what I'm going to do is I'm going to tell you that entropy, which is given the symbol S, is basically Q over T. So it turns out that entropy is a state variable, and it's a state variable in that basically if you have a reversible process, then the process doesn't matter. And in fact, the change in entropy will be zero. Since the change in entropy is zero, we've got the entropy at the end, which would be QL over TL. That's going to be equal to the entropy at the beginning, which will be QH over TH. So that means you can set QH over TH equal to QL over TL, and therefore you can replace QL over QH with TL over TH. That's the formula. Okay. They're going to derive it. That's what they're doing with all this stuff right here. But lo and behold, that's the equation, and the book made it really horribly disfigured. Let me see if I can not even spreading it makes it right. But this is the equation for Carnot engine efficiency. It's 1 minus TL over TH. Okay. That just comes from replacing the QL with a TL and the QH with a TH, which I told you is a ramification of the entropy not changing. So that's an easy way to quote unquote derive it if you wanted to, but I don't care about the derivation. I don't need you to do the derivation. I need you to be able to use that other form of efficiency and this form, 1 minus TL over TH. Now, you do need to understand that this is key to understanding what comes next. According to a theorem stated by Carnot, all reversible engines operating between the same two constant temperatures, TH and TL, have the same efficiency. Any irreversible engine, which means any real engine, operating between the same two fixed temperatures will have an efficiency less than this. That's key. So that's why I gave you that general formula for efficiency, work divided by QH. Okay. That efficiency can be used on any heat engine, period. If you go and calculate the Carnot efficiency on a heat engine, then you're going to use 1 minus TL over TH, and that'll give you the Carnot efficiency acting between those two temperatures. But you'll see that that is way, 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 way more efficient than what you get from the other formula. Okay. As I told you, another heat engine is the Stirling engine. There's another one called the OTTO cycle. Also, like the name of the dude that Tom Hanks played in A Man Named Otto. That's actually a German name, and I suspect, though I've never seen anybody write this down, I suspect that's how we got the word auto, AUTO, as in automobile. I could be wrong completely. I'm just assuming that, because this was the guy that gave us the Otto cycle, which was sort of the first big heat engine that worked great as a engine for a car and a train and stuff of that sort. And your book does do something with the Otto cycle. It doesn't do anything with the Stirling cycle. It might be in one of the problems at the end of the chapter, but that's about it. So there's 20-2 example. So that's another one that I told you you've got to know how to do. A very straightforward steam engine operates between 500 C and 270 C. What is the maximum possible efficiency? You just plug in 543. Notice you had to convert it to Kelvin. Divided by 773. Notice you had to convert that to Kelvin. And you got 0.3. That's the Carnot efficiency, 30% for a reversible friction-free engine. So you can imagine the actual car's efficiency is going to be way less than that. In fact, it says real engines might attain 70% of that 30%, which is about 21%. I once read, to give you an idea, I once read that GE and Philips, which makes steam turbines, they have some steam turbines that they've been working on now for decades, and they're reaching into the 40% efficiency. I suspect that's about as high as the mark as we're ever going to get. So just to give you an idea. Here's another one that's really nice. Again, this is example 20-3, which I already wrote down. Says a phony claim. An engine manufacturer makes the following claims. An engine's heat input per second is 9 kilojoules at 435 K. The heat output per second is 4 kilojoules at 285 K. Do you believe these claims? Well, what you're going to do is you're going to calculate the efficiency that works for all heat engines, which is work divided by the QH. But we don't have the work. What we do have is the heat input and the heat output. Well, remember the work is the QH minus QL. So we can do it that way, and that gives us 1 minus QL over QH. So when we do that, we get 56%. That's a pretty darn efficient engine, right? Now we calculate the exact same efficiency, but for a Carnot engine. And of course, with a Carnot engine, we don't use the inputs. We can just use the temperature. So when we put in 285 Kelvin and 435 Kelvin, we find the Carnot engine is only 0.34 or 34% efficient. So clearly, this person's either a charlatan or an idiot. He doesn't know. He doesn't know the difference, or he knows the difference and he's trying to rip you off. Okay. So if someone approaches you with an engine design that they want you to, give them a fund for, you can probably be sure if it violates the second law of thermodynamics that it's not going to be helpful. Okay. Exercise A, you can play around with. So here's the Kelvin-Planck statement of the second law of thermodynamics. This is another one you need to commit to memory. So make sure you do that. I am going to say it is no device is possible whose sole effect is to transform a given amount of heat completely into work. So remember me telling you about the engine where heat comes in and then out goes work. And if you don't have that leg where heat goes out, then it's not a possible engine. Boom, there it is. Okay, see how the heat coming in is, you need that, right? Work going out, it's not a heat engine. If it's not an engine, it's not useful at all if it's not putting out work. But notice it's not wasting any of the heat. None of the heat is going out this way. Therefore, it's an impossible engine. That's another second law of thermodynamics. Okay, and that's the Kelvin-Planck statement. It says with a little dagger here, 2 daggers that are important. One, a real irreversible process cannot be plotted on a PV diagram except approximately if it approaches an ideal reversible process. So that's just telling you the difference between them. If you wanted to know what that was about, they gave you a little footnote here. Really what I'm shooting for is this one right here, where it said if an engine had a higher efficiency than 23, it could be used in conjunction with a Carnot engine that is made to work in reverse as a refrigerator. If W was the same for both, the net result would be a flow of heat at a low temperature to a high temperature without being work being done. That would violate the Clausius statement. So it refers here to a third law of thermodynamics. So I just keep pointing that out just to remind you that you are supposed to know the third law of thermodynamics, which doesn't come up until section 2010. So there's the Otto cycle I told you about. Notice this is an isovolumetric process here and an isovolumetric process here. Going from C to D, again, this section is completely optional. I recommend you read it, but I'm not going to ask you any questions from it. But I just wanted you to see what it was. You can work out the process and find out what the efficiency is, but it doesn't matter because I'm not testing you on that. Here's where we talk about refrigerators and air conditioners. A refrigerator and air conditioner is basically a heat engine running backwards. Notice you've got work coming in, and we're drawing heat from the low temperature reservoir, and the work is combining with the low temperature heat to create Q high that's going to a high temperature reservoir. Okay. So this is in a refrigerator. This is you pulling heat out of the area where the food is. That's what TL is the area where the food is. It's pulling QL, but it can't just do that. It's got to have you put work into it, which would be like a fan sucking the air out, for instance, and then exposing it to something that could absorb some of that heat, and then that heat be expelled into your hot living room or kitchen, assuming you have it in your kitchen, of course. All right, so what they use there, like I said, is a coefficient of performance. I'm not requiring you to do any of that, but here's another statement of the Clausius second law of thermodynamics. Notice it's the same, it's a Clausius statement, and it's equivalent to the last one, but it's different, so you got to know it too. No device is possible whose sole effect is to transfer heat from one region at temperature TL, meaning a lower temperature, into a second region at a temperature higher TH. Okay, so you can see that is very much like the one we did initially, the very first second law of thermodynamics. There's the coefficient of performance, because really what matters is the QL. You really, at the end of the day, care how much heat you're pulling out of the cold space, and what it costs you is the W. Okay, so that's where the coefficient of performance came from. Again, I'm completely cool with you doing that in homework. I tried to get it out of the practice test, so you shouldn't have it there, but you might. Okay, but you will not have it on the test. So I just sent you that. This 20-5, that wasn't the one I meant. So yes, y'all can get rid of that. Let's see. I want to erase that, and it's not letting me do that. Okay, I did not mean to do that. I'm trying to erase this, and I don't think it'll let me. Nope, don't want that. Oh well. Okay, so ignore 20-5. This is one you actually did use the coefficient of performance for it. That's why I'm saying you don't have to do it. So no, you do not need to know example 20-5. You have to edit it from the toolbar on the left. Oh, okay, thank you. Appreciate that. So the toolbar on the left. Okay, that's not this one. See, reset. Hey, I don't know. That wasn't the right one. Whoa, I did it anyways. Okay, so we'll worry about that later, but you know that's there. Let's go on to the next section, which I think, yeah, this one's just if you're of the age where you're considering buying a house or already own a house, SEER rating is something that's important. You'll find out about it when you go to replace your heat and air unit. This actually explains to some extent what it's about. Again, it's a asterisk section, so I'm not requiring you to do it. Here's where entropy comes in. Notice the state variable entropy. You can write that as a delta S or a DS because that's actually allowed here, unlike the DQ and the DW. They had to be D bar Q and D bar W. This is delta S is equal to Q over T. And notice it has units of joules per Kelvin. That's a key thing to understand. It's called entropy, and a everyday word for entropy is disorder. So hopefully that'll give you some idea of what it's supposed to be. If you want to imagine something, this is kind of a decent example. I couldn't find something like this in a class the other day, but notice this right here. See how big this is? Imagine this is a parking space. Okay. Imagine this is a car. That's about the right size ratio for an actual car to an actual parking space, right? So when you think of entropy as disorder, one of the ways you might want to think of it is disorder is the number of ways you can follow a rule. Okay. So if you have a butt ton of ways you can follow a rule, that's a very disordered state. If you have a smaller number, then that's a fairly ordered state. And entropy is disorder. Okay. So just imagine, I want to imagine all the ways I can park in this parking space legally. So I can get my car completely up against that edge, and then I can move it a millimeter to the right, and then a millimeter and a millimeter. All those different places are ways that I can park legally. Now I can move it back a millimeter. And I can do that again, and then again, and again. And then I can start doing it sideways. And like this, as long as my edges aren't sticking out from the lines, I'm still in the parking space. So all of those different ways that I can fit this inside of this rectangle are the number of states in which I'm properly parked. So that's a fairly disordered state. You can see it's a huge number. But now imagine this. How many places can I pull out of the parking lot? In other words, if I pull out of the parking space, not the parking lot, sorry. If I pull out of the parking space, how many places are allowed? Well, there's one, there's one, there's all these for infinity, all this for infinity, turn this way. So basically, you've got an infinite number of places you can pull and not be in the parking space. So getting out of a parking space has way more disorder. And I've heard physics instructors use this before. Basically, the second law of thermodynamics is the reason it's easier to pull out of a parking space than it is to park. And hopefully you see that now because you see the number of ways you can park between the lines. And that's a big number, but it's nowhere near as big a number as the number of ways you can be out of the parking space. Okay. So hopefully that'll help you. This example 20-7 is definitely one we meant. So do no example 20-7. That was one that I put up earlier, but I've just wanted to reiterate that I hadn't made a mistake with that one. Okay. So it's a pretty straightforward one. The Q is obviously for ice, and it's just changing state. Notice it doesn't change temperature. Since that's the case, the Q is just M times the latent heat of fusion. So that's what the Q is. And then you divide it by the temperature at which it happened. That's the change in entropy. That's a positive change in entropy. So entropy increased, and entropy increases in naturally occurring phenomena, which is another version of the second law of thermodynamics, which we'll hit in a second. Okay. This little area right here, careful analysis, they actually do it on the next page, shows that entropy is a state variable. I thought you reading this might help you better understand, in case you didn't understand before, all the discussions I've had about why Q and W are not state variables, whereas pressure, volume, temperature, number of moles, or mass are state variables. Hopefully that'll help you. All right, let's kill this. You can see what I was talking about earlier. That's for the reversible process. The entropy doesn't change. So QL over TL is equal to QH over TH. that means you could pull the QH down here and you'd have QL over QH and pull the TL over here. That would be equal to TL over TH. That's why the Carnot efficiency is 1 minus TL over TH. So that's what I was showing you earlier. Again, the entropy is path independent. It's a state variable. And in fact, it doesn't change for a cyclic process because you're going from the same state to the initial state, back to the initial state again, I mean. This is the part you don't have to worry about. If you understand it, that'd be great. But right here, they do state one form of the third law of thermodynamics is as T approaches zero, the entropy approaches zero. So that's another version, or that's the first version you've actually been formally given for the third law of thermodynamics. So I highlighted it because you're supposed to know that. Let's go to entropy in the second law of thermodynamics. This might have been the one I meant. Let me see if there's an ice one. I thought there was an ice one over here. There's a free expansion. There's a heat transfer. Uh, I think, yeah, I don't want you to do 27. I don't mind 20-8. That's not bad. And 20-9 is a little more complicated than I want you to do, but 20-10 is fair game as well. So I'll just highlight these and say you really should know how to do these. So I highlight it, I share the note, I skip the free expansion, I highlight it, and I share the note. Now, I expect I probably will not ask you a question just like this, but I do think these are reasonable for you to be able to do on the tests. So I'm giving them to you. Okay. There's the free expansion. Let's show. Okay. Now here's a new version of the second law of thermodynamics. This is called the general statement. The total entropy of any system plus that of its environment increases as a result of any natural process. Natural means, of course, ones that do have friction. They can't be irreversible. They can't be reversible. They have to be irreversible, that sort of thing. And notice that it says the total delta S, the total change in entropy, is the delta S of the system plus the delta S of the environment, and that as a total is greater than zero. Although the entropy of one part of the universe may decrease in any process, the entropy of some other part of the universe always increases by a greater amount, so that the total entropy always increases. So one of the quote unquote charlatans that I occasionally bring up is people have made the claim that biological evolution, violates the second law of thermodynamics. This is the statement where you can clearly see that's not the case. You could have a group of cells come together and make a highly organized system, but the change in entropy for that is clearly going to be a decrease, whereas the change in entropy for the environment is going to be a net increase that overruns the amount of decrease that happened in the humans, because we've got this thing called the sun that provides us with a buttload of heat. Now, we've since also discovered that not all life on Earth needs the sun. We found that there's sub-ocean vents, and those species of life seem to have been created with never being exposed to the actual sun. So it just needs energy. And we could probably find out ultimately that the entropy there would decrease, obviously, in their evolution, but the entropy for the environment would increase to outmatch that. Any questions on that one? So there's another form of the second law of thermodynamics. We're almost done. I got one more neat thing to talk to you about. So this is time zero. It's a nice little paragraph. Basically, what it's saying is, in physics, we've discovered the only variable that tracks with time, meaning when it runs forward, time runs forward. When it runs backwards, time runs backwards. And when it sits still, time is sitting still. That only thing that we've ever found to do that has been basically entropy. So that's why people like Stephen Hawking and Brian Greene and Neil deGrasse Tyson, Michio Kaku, those guys talk about entropy as being times zero. That's why. But again, you can read it. Order to disorder. Here's another second law of thermodynamics. Natural processes move toward a state of greater disorder. There's the parking space, pulling in a parking space versus pulling out a parking place all over again. Now, this book goes through some really nice examples, and I would like you, I do want you to read it. This biological development is helpful. I do want you to read it, but I don't expect you to completely understand it, but I do want you to read it because I'm going to give you a neat little result. Both examples illustrate an important aspect of the second law of thermodynamics. In any natural process, some energy becomes unavailable to do work. That's what I was telling you about heat energy being a bastardized version. Energy is degraded. So that's why I highlighted that, just because that's such a good synopsis of the second law of thermodynamics and the imperfection of heat. It talks about the heat death of the universe. Again, not something I'm going to test you on, except maybe in the concepts. But here's the statistical interpretation that I'm going to try to explain to you to get this last result. We only got about 7 minutes. So imagine throwing 4 heads. Okay. You could say the number of microstates with 4 heads when you're throwing 4 coins is 1. So there's only one way you can throw 4 heads, and that's head, 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 head. Whereas if you wish to find out the number of microstates where you can throw 3 heads, well, that's head, 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 tail. That's head, head, tail, head. That's head, tail, head, head, or tail, head, head, head. So you get 4 microstates consistent with 3 heads. If you wanted 2 heads or more, you can see that you'd have 6 for 2 heads. 3 heads is more than 2, so that works as well. That brings me up to 10 because 6 plus 4 is 10. And then 4 heads is more than 2 as well, so that brings me up to 11. So there's 11 microstates that give us 2 or more heads. In fact, if you wanted to calculate the probability that you're going to get 2 or more heads, what you do is calculate all the number of outcomes. Well, the number of outcomes is 1 plus 4 plus 6, that's 11, plus 4, that's 15, plus 1, that's 16. So in fact, 6 plus 4 plus 1 is 11. So 11/16 is the probability of you getting 2 or more heads when you throw 4 coins at random. So that's how probability works. It's the number of ways of fitting the rule divided by the total number of outcomes. Okay. Now, with that in mind, you can try a really souped up addition. Okay. Let's imagine like we're starting to approach molecules. The number of molecules is like Avogadro's number. So when you start looking at things like molecules and atoms, you know you're going to be dealing with way more than 4 coins. In fact, what your book did here was let's figure out how many microstates are there for tossing 100 coins and getting 100 heads. Again, you might have suspected there's exactly one way. If you wanted to get 99 heads with 1 tail, there's 100 ways, and so on and so forth. So all these are little microstates. All this sounds kind of stupid, not necessarily useful, but you'd be surprised. It turns out this is really, really powerful. That Maxwell distribution that we did in chapter 17 or 18, that was really literally done by doing this kind of mathematics, which is just basic counting of combinatorics and stuff of that sort. So if you take that a little further, it turns out that Boltzmann showed, here's the most important part. Boltzmann showed, consistent with Clausius's definition of ds is equal to dq over t, that the entropy of a state in a given macro state can be written as the entropy is equal to there's the Boltzmann constant, so 1.3807 times 10 to the negative 23rd joules per Kelvin. So you take that and you multiply it by the natural log of W, and W is the number of microstates corresponding to the given macro state. So if you said the macro state, for instance, was 2 or more heads, then the number of microstates corresponding to that macro state would have been 11. So you take K times the natural log of 11 is sort of what they're saying here. Okay. W is called the thermodynamic probability or sometimes the disorder parameter, but that is like the big game changer. Okay. So I just wanted you to know that this equation exists. You should be able to state it and tell me what K is, and you should be able to define what W is. I don't expect you necessarily to understand the difference between microstates and macrostates, though I think the book did a really good job in explaining it. So I would say commit it to memory verbatim, because if you try to paraphrase, you might actually get it a little bit wrong. But if you have that in your brain, that'll allow you some time to make sense of it. And that's basically it. That's the entirety of chapter 20 that I care about. You can see this is stuff where I actually list the third law of thermodynamics. It is not possible to reach absolute zero in any finite number of processes. So that's the more compelling version of the third law of thermodynamics. That's one you should know. Thermal pollution, global warming. Again, highly recommend you read it. Not going to test you on it at all. If I did, it'd have to be like an extra credit or something. I might ask you, has any global circulation model ever produced a correct prediction? And I hope you now know that that is heck to the F. Any other questions? Any questions, period, I should say. All right. Well, we're done with chapter 20. Again, the examples were 20-1, 2, 3, and then 7. And then I showed you back here, I think 8 and 10. So I would recommend those, but I've highlighted them in the notes, so you should be able to see them as well, even if you don't remember them. See if I can find it. Maybe I'll type them out one more time just to make sure you guys are all on the same page. Yes. Examples 20-1, 2, 3, 7, and then 8, and I think 9, 10, excuse me, 8 and 10. All right, so look for my highlights. Anybody have any questions? All right, so this homework, you should be able to get it done by Sunday. We're actually going to meet again too, so you have plenty of time to ask me questions on Thursday. So make sure you've attempted those before then, so you can ask me questions. Because chances are I'm not going to be replying over the weekend. But you know, if you do, and I happen to notice it, then I'll do my best. But like I said, this will be your chance to get help. So everybody's free to go. I'll wait for the last person to leave. Oh, those of you who haven't left yet, please, I know one that already left, so I caught her. That's not a problem. So yeah, please text or chat to me your first and last name, so I'll do it as roll. I think that's the only person that left so far, and that looks like the number. So yeah, just make sure you text me your first and last name. Carly, did you get my email, by the way?
Yeah, I did.
Okay.
So I saw it this morning,
No problem. Did you
right
send?
before class.
Make sure you send me an email, and we'll discuss that. Okay.
Okay, thank you.
Okay. See you. Anybody else? Oh, Shonda was here. I thought she left. It might have been someone else that left. So, anybody that left, if you see this, make sure you send me an email, let me know. If y'all know who left, please tell them so they can send me an email and I'll get their name. It doesn't really matter too much. I don't kick people out for missing class, but have a good day, everyone. Bye-bye.